So in blast furnace, as we know, the top gas is not just a exhaust. It is the forensic signature of every reaction happening inside the stack. Look at the central wireframe visual. Notice the orange hint bloom in the hearth at the 1255 degrees Celsius versus the cool exhaust plum. Today we are going to move beyond reactive operation. By the end of this session, you will gain three specific deliverables. First, the ability to read the chemical signature of the vertical journey. Second, a journey, or we can say a strategy to map 3D scaffolding using 2D thermal radar. And finally, the exhaust mathematical key to closed loop thermal anticipation. So we are not just watching a black box anymore, we are decoding it. To decode the result at the top, we must first understand the high speed kinetics of the journey from bottom. Now look at the wireframe furnace on the right. In the in a less than 10 seconds, the blast gas cooled by 2000 degrees, leaving behind the entire chemical history. Follow the blue arrow from the engine at 20 to 100 degrees up to the exhaust at 150 degrees. Note the specific reaction zone. At 2 seconds, we are in the crucible at 1000 degree where woodite reacts endothermically. By 4 seconds, magnetite reduction is in full swing at 600 degrees. The so what here is the critical. Every degree of cooling and every molecule of CO converted is a data point. If the gas reaches the top too hot or too rich in CO, you are not just losing heat, you are literally blowing money out of the stack. That loss of money is quantified by one single vital metric, the gas utilization efficiency. On the left, you see a visualization of an invisible plum. The red spheres represent oxygen within the burden, while the blue and the magnetous arrows shows the gas paths. So look at the utilization panel here, equals CO2 divided by the sum of CO and CO2. We are targeting a state of 45 to 50% efficiency. The forensic takeaway on the bottom right is your operational mandate. Higher CO2 at the top proves you are perform aggressive oxygen extraction from the burden. This reduces the need for expensive endothermic direct reduction in the hearth. If your CO2 level drops, your fuel rate must rise to compensate. It's a direct mathematical trade-off that impact your bottom line every single hour. Beyond simple efficiency, we must monitor the physical plateaus where this reaction stabilizes, that is the reserve zone. So this graph is your furnace health chart. Follow the red temperature line on the left. Notice those two flat plateaus highlighted in red and blue, the thermal and chemical reserve zone. The diagnostic insight here is a warning. The disappearance of that thermal reserve zone plateau is the first invisible sign of an overpushed furnace. When you push productivity too hard, the furnace loses its stabilizing inertia. Notice the efficiency markers on the right side y-axis. As those zones shrink, your control over the process evaporates. Operationally, if those plateaus start to tilt or vanish, you are heading towards thermal instability. You have to respect the thermodynamics of the stack, or the stack will stop respecting your production targets. While these zones are vertical, we also face horizontal threats like scaffolding that can be detected via thermal radar. Now, as you can see, the 2D surface detection of 3D scaffolding. So look at this 2D thermal radar on the left. The deep blue crescent at the 270 degrees mark indicate a cold spot. Now look at the 3D cross section on the right. That cold spot perfectly mirrors a scaffold or solid accretion clinging to the wall. Notice how the gas shown in the magenta arrow is forced to channel on the opposite side. On the scaffold side, you will see low gas velocity and low CO2. On the channeling side, you will see high top temperature and erratic burden descent. The so what factor is clear. A cold surface doesn't mean a cool furnace. It means a block depth. If you don't clear that scaffold, you will eventually burn out of your steps on the opposite side due to channeling. Detecting blockages is a step 1. A step 2 is mastering the aerodynamic fingerprint of your gas flow. So now coming to the aerodynamic fingerprint gas flow distribution matrix. So this matrix displays the 4 aerodynamic fingerprint. We have the type 1 U shape, the type 2 W shape, the type 3 bell shape, and the type 4 flat line. Look closely at the type 3, the bell shape highlighted in the amber yellow. This is your ideal operational state. It provides a central coke chimney which is required for high pulverized coal injection and alkali removal. Note the risk factor below. Type 1 and 2 carry high wall erosion risk, while type 4 shows dangerously low gas utilization. To protect your copper steps and maintain high PCI rate, you must force the gas into that central bell shape. Anything else is a compromise that risks the physical integrity of the furnace shell. Once we master the flow, we can use the anticipation matrix to see a hearth freeze before it happens. Now coming to the thermal state anticipation matrix. Now this matrix is the forensic reality of iron making. Look at the transition from run hot in orange to freezing in dark blue. Notice the top gas signals. As we move toward a freeze, top gas temperature uh, uh, changes, while the CO2 ratio shows a sharp spike. The most critical insight here is that 6 to 8 hours delay because of a structural inertia, your top gas will tell you the furnace is running cool hours before the molten metal temperature actually drops. So by monitoring the pressure drop and the permeability index shown in the table, you can prevent a catastrophic hearth freeze while the metal is still technically hot. So don't look at the taphole for thermal state, look at the top gas. This lead time allow us to engage the ultimate tool in modern iron making, the closed loop engine. Now coming to the our next slide, which is on the closed loop anticipation engine. So as you can see, uh, all this is the summary and which is to be concluded with the closed loop anticipation engine. On the left, the top loop observes the physical feedback using gas analyzers and radar probes. This data enters the black box or mathematical mass and heat balance model. The bottom loop then executes the intervention adjusting blast volume, oxygen enrichment or PCI rates Remember, top gas forensic is not just a historical record of what was the burn. It is the exact mathematical key to controlling what will burn. Anticipation is the difference between a manager who react to a crisis and a master who prevent one. So let's take these forensic tools back to the floor and start running our furnaces with the professional precision.